Okay, this is the systems of equations section. One of your last sections, so you're almost done. So a system of equations is going to be two or more equations that you're trying to solve for the missing variables. You can graph them on the same coordinate plane. So you could have a set of two equations with two variables, three equations with three variables, etc. And to find the solution to the system, think of a graph. You can have two straight lines, and those two straight lines can intersect at one point, which is this idea of a one solution. So that's where they're physically interacting, and one solution makes all of the equations true. You can have no solution, meaning there's not a way to make all of the equations equal, or you can have an infinite number of solutions, meaning there's lots of different numbers that all make it true. So with that in mind, we have a little bit of terminology here. One is consistent. That's a system that has at least one solution. So one solution and infinite solutions are what's known as consistent. Now to add to that, if you have one solution, you're known as independent. So consistent and independent. If you have infinite, you're dependent. Right? So just a little bit of vocab there. So within a consistent system, be consistent because you have a solution. Independent is just one solution, independent of the others. Dependent, you have several things depending, so it's an infinite number. And then the other type is this inconsistent, and that's your no solution ones. So inconsistent means you cannot find a solution that's going to make all of the equations equal or true. All right, clearing that for a second. Okay, so I have a chart graphically to explain these. So on a graph, you would have two lines, or you could have three if you have three equations, etc. So if you have exactly one solution, that means your lines would hit at exactly one point. If you had a third system, it might go like that, and it would still hit at that one point. So again, consistent and independent. Independent thinking you're all by yourself, just one. If you're inconsistent, that means no solution, meaning they never intersect. These are going to be those parallel lines. So parallel lines have the same slope and they never actually touch. Therefore, you'll never be able to get a solution out of it. And we call those inconsistent. And then infinitely many may be hard to see. It's because you're the same line. So there's all these different points that could be answers, and that still gives you consistent because there is a solution, but it's called dependent. I think there's lots of pieces in there, and that's when you have infinite. So you might want to kind of add those to your notes. Think about those for a second. I'm going to clear. So with that in mind, we have three methods for figuring out a system of equations. You can do what's called this graphical approach, meaning you graph it and you either find the point where they intersect, you realize they never intersect, or you realize they're the same line. And then elimination and substitution are algebra based. So we are going to go through each type. And just remember there's three different possibilities: exactly one solution, no solution, and infinitely many as we go. Okay, so your first one is going to be graphing. Okay, so if you take a look, what we're going to do with graphing is you're going to graph one equation. Graph it as clearly as you can. Use graph paper if you can. So 2x minus 7 means it starts at the 7. -7, I'm sorry. And then it goes up to over 1. So you would go 1, 2, 1, 1, 2, 1, and just try to be as consistent as possible with the graph, because the idea is you're trying to actually see where that solution hits. And then you're going to go to the second one and graph it as well. So the +1 is where this one starts. Oops, off a little bit. And then it goes up to over 3, up to over 3. And then ideally, you'd be able to get that point off of there, which is 6, 5. And once you have all that, you do want to always make sure that you plug them back in and make sure they really work for both, especially with graphing, just in case something got a little bit off. So what I mean by that is I'm going to add a step D, which is check your work. Sorry, it's a bit rough on this. So first graph one, then graph the other, then see where they intersect, if at all. And then check your work. So we have this equation 6, 5. So I'm going to put in 5 equals 2 times 6 minus 7. 12 minus 7 is 5. And then 5 equals 2/3 6 plus 1. 4 plus 1 is 5. And it can be that easy to just check your work and make sure it works. It has to work in both, just as an FYI. It will work in both equations. Okay, I'm going to go on to example 2. So if you need a minute, pause me. Okay, and again, this one is a consistent, independent solution. Consistent and independent. Okay, one solution, consistent and independent. When we go to graph example 2, all right, probably the best thing to do would be put this in slope-intercept form. So I would divide by the 9. So that gives me 19x minus 27/9 equals y. So I divide it across. That gives me 19x minus 3 equals y. Okay, so I go down to the minus 3, and we'll look at that in a second. For my other one, I'm going to move the x over. So that would give me negative x plus 18 equals negative 9y. And then I'm going to divide by the negative 9 so that this looks nice. So that one is 19x minus 2 equals y. Okay, let's think about that. So I've got one starting at negative 2, one starting at negative 3. And each time they're going to go up 1 over 9, up 1 over 9. Then this one's going to go up 1 over 9. This one's going to do the same. If they have the same slope and different starting points, they're never going to hit because they're both going up and over at the same rate. So that same slope means these are parallel. And what does that mean? So this one has no solution and it is inconsistent. No solution, inconsistent, because they were parallel lines. And you could tell from the slope that they were going to be that way. Okay, I'm getting ready to clear this, so pause if you need. And then our last one, if we solve for y, this one is already done. So let's solve this one for y, just because that slope intercept form of y equals mx plus b is probably going to be our best way to graph it versus trying to do intercepts, because unless the intercepts are the answers. So let's see, we're going to move the 2x over. Okay, so that gives me 3y equals negative 2x plus 15. Then we're going to divide by 3. That gives me y equals negative 2/3 x plus 5. What's that look like? So that is the exact same equation. So that is going to graph as one line. In that case, this one is consistent, dependent, and has infinite solutions. Okay, so one of each type with our graphing. Okay, so then besides graphically, we have substitution and we have elimination, which are both more of a little bit algebra. So let's kind of walk through those steps and then we can try a few. So if you can, you want to solve at least one equation for one variable. That means getting either the y by itself or the x by itself in at least one equation. It's usually easiest to do that if you're looking at a variable that would just take one step to isolate. If not, you do multiple steps. So as I go through these, I'm going to work through this example. So solve at least one equation for one variable. So this one, it would be easiest to move that 2x over. Okay. So if I do that part, this next piece says substitute the result into the other equation. So this is y now. So over here, in place of y, I'm going to write the equation out, but y is now going to be parentheses. In that parentheses, I'm going to put that y, which is now 2x plus 4. And the reason I do that is now I have this all in terms of x, one equation, one variable, I can solve it. So next, I solve that equation. So this gives me 8x, I'm going to take those over, plus 10x plus 20 equals 2. 18x plus 20 equals 2 minus your 20. And we get 18x equals negative 18. So x is equal to negative 1. Okay, got all that. And pause there and work through that algebra, make sure it makes sense. Make sure you're distributing so that you're not just getting lost. Now substitute that value into this first equation. So we now have x is negative 1, y is 2 times x plus 4, making y 2. So from there, I solved for the other variable, and now I can write the solution as an ordered pair. And again, make sure that you put it back into the original equation. Make sure it works for both of them. So 8 times 2 plus 5 times negative 1. That's 16. Oops, sorry about that. That's 8 times negative 1 plus 5 times 2. So that's negative 8 plus 10 is 2. And then negative 2 times negative 1 plus 2, 2 plus 2 is 4. So this one does work. It is a solution. We're getting a consistent, independent solution. Okay, so moving on to our second one. Make sure you have these steps copied down, and then we're going to walk through for number 2. Okay, so for example 2. Okay, so again, we're going to solve one for one variable. This x has the least amount of stuff with it versus x and y over here would need a few steps. So what I'm going to do here is actually divide the whole equation by negative 1. Because what that's going to do is give me, just right, x is going to be equal to y plus 4. Okay, so I've divided everything by negative 1. Then for my next step, I'm going to take that and plug it into the x here. So negative 2x plus 2y equals negative 4. And in place of that, I'm going to put y plus 4 in there. Okay, so far so good. And then we're going to solve that equation for y, one equation, one variable. Make sure that you're distributing. So it's negative 2y minus 8 plus 2y equals negative 4. Those y's will cancel, and you're left with this negative 4 equals negative 8 piece. That's not possible. They are not equal to each other. This tells you that you have that no solution. Those two must be parallel. They are inconsistent. No solution is going to make both of those true because -4 is not negative. Okay, and down here on the bottom, let's give this one a go. Okay, so if we solve this one, let's see, looks like the y is going to be the easiest. So I'm going to subtract the 2x from both sides. Oh, keeps going to my spotlight, I guess. Okay, that's going to give me y equals -2x plus 5. So now we take that and plug it in to this one. So negative, what is it doing? -6x minus 3y equals -15. And we're going to put in that -2x plus 5 component. So that gives me -6x plus 6x. Oh my goodness, what is this doing? Plus 6x minus 15 equals -15. The x's cancel. Put 6 in, take 6 out. So you are left with a true statement that says -15 equals -15. Any number is going to make that true. These were actually the same versions of each other. If you multiplied it by -3, same equation. So therefore, this one has infinite solutions because no matter what you put in for x, it'll cancel out. This is consistent, dependent. Okay, so different types. If you come out with one solution, you have it. If you come out with an untrue statement, like in example 2, there's no solution. If you come out with a true statement, there's. All right, pause if you need to. I am going to clear the page and do the last one, which is elimination. Okay, so for elimination, what you do is you align the terms first. So all like terms are aligned, meaning right here, x's go y equals numbers. It's easiest to align them with x, y numbers, but just make sure they're aligned. Then you make it so that at least one set is opposite. What that means is that if the top has a -7x, you want the bottom to have a 7x. Or if you want the y's to cancel, if one's a y, the other needs to be a -y. So you want one set of opposite terms, more is fine, but at least one. Then you add them vertically, which will cancel out a term, hopefully, if you did it right. Solve for the remaining variable, and then do that substitution to get it back. Okay, so I'm going to leave those steps there, and we're going to give this a go. All right, so again, write both equations so that they're aligned. Check x, y numbers. Multiply to get exactly opposite. So 6 and 4 don't have an easy multiplication, but 14 and 7 do. So I'm going to multiply this one by 2. So that's going to give me the 6x plus 14y equals 6. Nothing changed. And then it's going to give me -8x minus 14y equals 22. Make sure to multiply that 2 by every piece. Now we do step C, which is add them vertically. And this is fine to do. We're adding them. It's going to give me -2x. Something should cancel, or you did it wrong. This should be a -22, shouldn't it? Gives me -16. So I come up with x equals 8. Sorry about that. Okay. Okay, let me me write that off to the side so that doesn't take so much room. So we come up with x equals 8. Then substitute that into either one of the equations, really. It doesn't matter which one. It should give you the same answer either way, and solve for the other variable. So I'm just going to put it into the top one. 6 times 8 plus 14y equals -6. So 48 plus 14y equals -6 minus the 48. That's a +6, I apologize. So I get 14y, -42, which gives me y equals -3. Then I mentioned write the solution as an ordered pair. And if you're asked for an ordered pair, make sure you write it as an ordered pair with x first and then y. And again, I'm going to add another one, and that's that you should always check your work. It's math. We can check that it works. So I'm going to erase a little bit down here. Okay. And let's just quickly check that all this makes sense. Gosh, it's taking quite a minute to erase. Okay. All right, so for that check step, again, if I put these in, they should come up with a true statement. Okay, so 6 times 8 plus 14 times -3. 48 minus 42 is 6. Perfect. And then we're going to do it in the bottom one. Okay, -32 plus 21 is -11. So that one worked as well. So 8, -3 is our solution, and we're happy. So if you come up with one solution, it means consistent and independent. All good. One spot where they would touch. All right, pause if you need to write. I'm going to keep going. So for example 2, possibly 3, let's see if we can get that one in there too. Okay, so for example 2, you can either do, let's see, 8 to 4, either one is fine. Let's do the bottom one. Let's times it by -2 because I want these to be opposite. So that gives me up top 8x, -8x plus 2y equals -10. -2 times -4 is 8x. I wanted them to be opposite. Oh, but then keep going. Okay, now we add them together. So if you're not sure on that step what to multiply by, you want something to be opposite. So -8x and 8x, because when you cancel them, or when you add them together, they'll cancel. The idea is you want to cancel out at least one variable, or you're not really getting anywhere. So when I add these together, -8 and 8 is 0, 2 and -2 is 0, and this is -6. 0 is not -6, so this is an example of a no solution. This is an inconsistent no solution. And then we'll go down here. All right, 6 to -3, so I'm going to multiply by 2. So that leaves me with 6x plus 8y equals -28. All right, so 2 times -3 is -6. That's why I multiplied by it. I wanted those to cancel. But 2 times -4 is also -8, and that is 28. So down here, when I add them, 0, 0 equals 0. Well, 0 does equal 0. So when all the variables cancel out and you get 0 equals 0, that is the infinite solution. Okay, that means it's consistent but dependent. All right, that's your crash course on systems.